All right, thank you very much for the introduction. And yeah, this is my kind of great honor to introduce you our kind of recent progress. So first of all, I would like to thank all the PIs, postdocs, and other administration staffs who are contributing and tackled with the really high risk, challenging research topic. So our grand vision is a society free from the fears of extreme hydrometeorological disasters by controlling not only weather, but also society system based on the democratic social decision making. So specifically, we have basically two challenges. So each one of the PIs are allocated into either A or B. So A is a meteorological control theory. We have the theoretical advancements to achieve the weather control. And then on the other hand, the B is the impact forecasting of disaster, because if you don't understand how society responds to the disaster, you cannot design what kinds of control is best for the mankind, right? So I would like to start from this topic A. So it is very likely that the weather or atmosphere is a chaotic system, characterized by the strong sensitivity to the initial condition. So it, as the Sebastian and Miyoshi-san discussed, it may bring some controllability. So if you slightly move from blue to red by the human power, that difference will grow into the future so that you can get some large difference. So this is quite a classical idea, but we do not test. We didn't test it in the weather control context. So I believe that not only the weather control, but also in any modern scientific disciplines has two different approaches to tackle with the problem. First one is a process-driven approach. So based on your understanding of the physical phenomena, you're going to come up with some idea and test it. So this approach is more like a bottom-up way. And there are a lot of works in the process-driven approach in the weather or typhoon control, but actually there's no work which focus on the chaos control. So that's one problem. And the other approach is a data-driven approach. So in the data-driven approach, basically we specify the goal, and then we're going to automatically derive when, where, and how to intervene in the system. So it's more like a top-down approach. Unfortunately, I think as far as I know, before the Moonshot, there's quite a few work which use the data-driven approach to modify the weather. So that's also quite problematic, right? So let's first focus on the process-driven approach, our process-driven approach. And our platform is the convective scale, the tropical cyclone simulation based on the meteorological model and the all-sky geostationary satellite data simulation, okay? I mean, all-sky geostationary satellite observation, all right? So why do we need a convection-resolved tropical cyclone simulation? Because we believe that this convection, each one of the convection is the engine of the chaotic growth of the tropical cyclone. So that's why we have to resolve it, and then we have to analyze each one of the convective activities in the tropical cyclones. So we did it. So this is the composite of each one of the convective activities within the tropical cyclone, and then we decompose that composite into the several spatial scales. And we found that we have a robust convergence of the water vapor only in the space. Oh, it's quite a high tech. All right. Okay. I don't use it. So in the third from the left panel shows that you have quite a robust convergence in the specific scale, which is a 20 kilometer and 200 kilometers. Okay, so that's a robust moisture convergence. So although it is, of course, technologically impossible, but what if only this convergence is smoothed out in the typhoon center? Because we believe that the convective activity is the engine, and then this convergence is the engine of the convection activities. So our hypothesis is that if you do not have this kind of convergence although the total amount of water doesn't change, but if you smooth out these kinds of convergence, tropical cyclone will disappear. And this is right. So here in the bottom, the time series, the black line is the original tropical cyclone simulation. It's quite strong. I think it is the Harvey, right? And then the red line is that we just smooth out the moisture in the specific scales that we found in the previous slide. So there's no tropical cyclone literally. If you start in the very beginning of the tropical cyclone initiations. All right? So, but again, of course, this is not technologically possible. So how does this kind of theory enable the realistic interventions? So to do that, we are now focusing on the data-driven approach. And our approach is the ensemble command control, or ENKC. So basically, we're going to use the ensemble command filter, which is a quite a widely used data assimilation, twice. Once for the state estimation, and then the second for the control. So yeah, we literally use the duality that was discussed in the previous talks. But I also propose some kind of unified framework to solve both the prediction and the control problem. So first ensemble command filter is a conventional ensemble command filter. So we're going to integrate the observation into the state variable, and then we can get the so-called ensemble analysis ensemble. And then from that ensemble, we're going to perform the extended forecast. And if we can find a good operator, you can evaluate each one of the extended forecast ensembles. So we can compare your extended forecast and the control goal, okay? And then the theory says that what you should do is just to assimilate this control goal using by recognizing it as a pseudo observation, okay? So this is very, I think, useful because primarily because that you can use a lot of infrastructure of the ensemble command filter. So ensemble command filter is quite well known and it works in the earth scientific problem. So we can use that infrastructure for the control. So that's why it's quite easy to extend. And then you can have a lot of idea to further improve the efficiency of the control. So we perform the idealized tropical cyclone experiment. So we apply the ENKC every 1 hour. So we perform the extended forecast every 1 hour, and then we decide where to intervene every 1 hour. And our control target is, of course, we would like to increase the typhoon central pressure. So we have a prescribed level of the typhoon central pressure, and we try to achieve it. ENKC try to achieve it. Okay, and also we have some constraint because you cannot change it anywhere, right? So we constrain the perturbation, just the water vapor in the lowest atmospheric level. Okay, actually some engineers try to modify this kind of lowest water vapor by modifying the surface flux. So for instance, changing the sea surface temperature or spreading some surfactants, okay? And then, honestly, this experiment still does not derive any kind of the operationally possible methods, but we would like to answer those kinds of questions. Where should I intervene? And also, how small-scale intervention is while maintaining the same level of mitigation. So let's see. So because due to the time limitation, I cannot explain this hyperparameter, lambda, but this lambda controls the scales of the intervention. And so this is the 2,000 kilometer model domain, and the tropical cyclone is located in the center, and it doesn't move. So TC always located in the center of this domain. And the black dot indicates a strong convective area, so it's kind of the eye wall. And the blue shade is the ENKC estimated water vapor reduction. So if you look at the lambda equals to 0, you have quite a large area is modified. But if you increase the lambda, you can see, I think, for instance, in the lambda 0.95 case, maybe it's difficult for you to find where to intervene, right? Because it is very small. And this is a movie, so let's go. So the ENKC automatically determined where to intervene in the counterclockwise way. okay? And again, if you look at the larger lambda, it's very difficult to see the location of, it's not so much tricky, but it's quite, the intervention scale is quite small. And this is a snapshot. So again, if you use the larger lambda, you can effectively reduce the intervention and the magnitude of the interventions, okay? And then with large lambda, intervention scale is approximately the order of 100 square kilometers. So 100 square kilometer intervention, it's not so realistic, honestly. But you should be noted that we are now using a 5-kilometer model, so that each one of the pixel, the size is a 25 square kilometer. So that you cannot resolve the smaller scale than that. So I believe we are now actually reach the limit. So you cannot expect that the more like a smaller intervention scale unless we're going to use the more like a finer resolution model. So that's the direction we should go in the future. And then this is kind of a summary of the total amount of water vapor reduction. We continue the intervention 72 hours. So this is a 72-hour total water vapor reduction. And then, yeah, again, in the larger lambda, the scale of the intervention is really small. And then I think one of the interesting finding is that on average, we should intervene at the 200 kilometers from center. So we initially thought we have to directly go to the eye wall. However, ENKC prefer to intervene a bit far from the eye wall, and then they prefer to propagate that intervention on the floor of the tropical cyclone. They think they kind of think that choice is much more safer to avoid the strongly nonlinear and unpredictable processes. And then maybe you might be interested in how much impact we can get. So this is the impact of control on the tropical cyclone intensity. So left figure shows the time series of the minimum sea level pressure, and then right figure shows the maximum 10-meter wind speed. So you can see the thick black line is uncontrolled nature, but the other colored line is a controlled nature. So except for the largest lambda, which means that we perform the smallest intervention, all the other experiments successfully increase the mean sea level pressure. And although the amount of the hectopascal is not so large, but if you translate it into the maximum 10-meter wind speed, sometimes we can get the more than 5 meter per sec reduction of the maximum wind speed. So not that bad, I think. So, but you can see the larger, if you use a larger lambda, you need more time to find the significant effects of intervention. Because under the larger lambda, they prefer to intervene a bit far from the TC center, so that it's going to take time to get some evident impact on the structure of the tropical cyclone. And then, yeah, although I don't have much time to explain that, but we are now investigating the mechanistic understanding of why this intervention can mitigate the tropical cyclones. So basically, their perturbation will eventually reach to the eye wall, and then you can see the significant reduction of the hydrometer on the eye wall in the successful control simulation. And then it also brings some mitigation or reduction of the strong secondary flow. Okay, so we are actually reaching the engine of the tropical cyclones that I discussed in the previous part of this talk. Okay, so this is really, our result is really consistent to what we found in the process-driven approach. But point is that I didn't tell it to the ENKC. So ENKC automatically suggest us to these kinds of the perturbations. So this is indeed data-driven or top-down exploration of the controllability. Okay, so now we have both data-driven and process-driven and the data-driven approach. So of course, this data-driven approach is not just the achievement of my project. Yesterday, I hosted the mini workshop on the mathematical weather control methods. So there's a lot of idea to accomplish the weather control by the data-driven approach. You set the goal and automatically derive where the appropriate perturbations. Okay, so before the moonshot, you have only the data-driven approach. So you have only one wing. As far as I know, all birds need two wings to fly, right? So now in the moonshot, you have two wings. So we can fly now. You can fly now. So I really believe that the future is really bright. So we are ready to lift off, okay? But I think one of the most easiest criticism on this approach is that you are using model, and the model is always wrong, right? So we are now also carrying these kinds of points. So we have a large uncertainty in our atmospheric model. So okay, although you think that blue line is a business as usual, but it is estimated by the wrong model. So if the real nature is green, you cannot accurately control the system, right? So we are trying to quantify the uncertainty of the atmospheric model, specifically the parameterization selection. So we are working with the people in the Vietnam operational weather agency. So they are now having the physical ensemble, so which means that they choose the different combination of the atmospheric physical schemes. But our idea is not instead of choosing the schemes in the discretized way, but we blended and then try to optimize how to blend in different schemes. Okay, so we blend the schemes in each one of the model time step. So it's a bit complicated problem, but with the help of the machine learning, we just optimize these kinds of the how to blend the different schemes. Okay. And then you can see that blended parameterization can be transferred to the new severe rainfall events. So I mean that it literally outperformed the operational system in the Vietnam. So yeah, as you know, the Moonshot is the national flagship project. So that, of course, we have to pursue the kind of fundamental, far-reaching science. But at the same time, I believe that I am responsible to help more like a practical problem. So this is one of the important social impact of the Moonshot project, because we are now helping the operational forecasters, right? So, okay, I'm speaking too fast. Okay, but all right, but let's move on to the section B. Okay, I thought that, yeah, all right, but anyway, okay. So I have some kind of vision on that topic. I mean, the weather and the society. So I think actually many studies think that you may have a fixed society, and you change the weather, or you change some infrastructure, and then evaluate the impact of such kind of policy on the society. I don't think it is not enough, because if you change the policy, society responds to it, right? So if you understand, okay, weather control is incoming, maybe your behavior might be changed, society might be changed. So we have to see these kinds of interactions as a dynamical system. Okay, so that's our kind of, I'm recently advertising this word, sociometeorology. And to advance such kind of vision, of course, it is very important to estimate the hazard impact. So we are now, I'm often saying that let's translate weather to disaster more precisely, but quickly, because we need, of course, the real-time capability. So we have a lot of wide aspects of the hazard estimation, such as river, ocean, strong wind, gust wind, or something like that. But I just would like to bring one example. This is the global flood forecasting system with the explicit consideration of levee. So it's not so big deal to just focus on the one river basin. You can collect some local data of the location and the height of the levee. But however, using the machine learning, we can get the levee location and its height in the whole globe at the same time. And we can compute the flood inundation, considering the levee effects, in the global, in a quite a computationally efficient way. And we have quite an evident impact of the levee. So especially when you evaluate the smaller scale floods, the levee function is really important, but you can evaluate it. And by integrating those kind of technology, we can perform the super large ensemble forecasting of the typhoon-induced hazard. So we can realize the scenario-based analysis. So we are not focusing on the single hazard, but we are focusing on the many like a hazard, storm surge, flood, and gust wind in the many different locations. So in that case, actually the worst case scenario, choosing the worst case scenario is a bit complicated problem because we have a trade-off, right? So that this is kind of the multi-objective problem. So we use some mathematics on the Pareto optimality. We can objectively choose the many worst case scenario from the data. So those kinds of the ensemble, how to use the ensemble forecast is really kind of practically important topics. So again, I believe that of course this is a fundamental research, so I cannot directly have some impact on the society, but we are pursuing some more immediate social impact in the Moonshot project. And another important finding recently is that how forecast changes the society. That's the question. So once again, I think I recognize the society as a dynamical system. So if the weather agency issues a forecast, you change the society, right? So one of the important questions in this community is the cry-wolf effect is really exists or not. So cry-wolf effect, it means that if for instance, some weather agency issues a false alarms, and people will stop trusting such kinds of the agency, and then they don't hear anything about the warnings. So that's a cry-wolf effect. It is quite a controversial topic, if really it exists or not. And we got the first ever evidence of the cry-wolf effect in the flood forecasting. So again, if the agency fail to accurately deliver the prediction, actually they change the society. So we have a lot of case study evidence, as well as quite a large data, 7,694 floods in Japan, large data evidence. So yeah, apparently I believe that it has quite important policy implications. And lastly, I would like to, still I'm too fast, okay. I'm gonna close the talk. You were saying the LC. So yeah, LC point is really important, and our focus is that the LC points from experts as well as non-experts. So as they contradict with each other. And then our method is just to go there, go to the people and directly talk with them. So we are correcting and comparing LC points from experts and non-experts via dialogues and discussions. And we have LC research, but we also have the LC-driven research. So in these kinds of LC activities, scientists actually come up with some important research topic. So I would like to explain some example. So when I joined these kinds of the dialogue, I was often asked, what kinds of TC, tropical cyclones, should be controlled? Okay, so which one of the tropical cyclones should be controlled? That cannot be determined just by the natural science. So that's quite a social issue. So my postdoc come up with quite an interesting idea to generate the tropical cyclone ranking. All right, so let's have a ranking, but under the multi-dimensional framework, because the social impact of a tropical cyclone is quite a multifaceted. So here this ranking is sorted by the economic loss. So Hagevis is a number one. So there's quite a huge economic loss, but actually the damage should not be measured just by the economic loss. We have a household, the loss of the households, or casualties, or deaths, or many kinds of measures. So we put all of them and perform the Pareto optimality, Pareto multidimensional analysis, and to see there's multiple number one. So if you do that, we can find that there's a lot of tropical cyclone which is economically less impactful but substantially damaging. Those kinds of tropical cyclones often hit the rural area. Because rural areas, there's no kind of large economic assets, but people there, so people are killed, right? And although I don't have enough courage to show it in the slide, but actually we also found that the scientists tend to investigate the economically impactful tropical cyclone. All right? So those kinds of the economically less impactful but substantially damaging tropical cyclone was not chosen by the scientist as a case study. So yeah, we often say that weather control or our technology, of course, is not just for the Tokyo. We would like to save all of the people, right? But do we act in that principle? We should ask ourselves, right? So this is also, I believe, another social impact or contribution to the practitioners. All right, so this is a wrap up. So yeah, this is we have quite a multi-dimensional research toward the controllable weather and society. Thank you very much.
Okay, thank you very much, Dr. Sawada. Now open for questions. On-site or online, both sides. Any comment? Yes?
So you decided the ranking of the impactful typhoons, not purely based on economic loss. Could you tell me what did you consider to make the ranking?
Yeah, so I think that for the social impact, there's three measures. The one is an economic loss, and the other is the casualties, so injuries and the deaths. And then the household damage, the number of households destroyed. And then,
sorry. Let me rephrase what I asked. So you sorted the economic loss order, but you have some other measure, single number showing, single value showing. So do you have some equation or whatever?
Yeah, we were standing on the Pareto optimality, which is often used for the economics. So we have two different the measures. So for instance, okay, if my math score is 50, and then the English score is 50, and then your score is 70 and 70, so in that case, you beat me. However, if your math score is 70, but your English score is 30, I know your English is really good, but your English score is 30, so in that case, each one of us cannot beat completely. So in that case, we are both number one. So that's the measure of the Pareto optimality. Yeah, I know it's complicated.
So it's not like you have multiple measures to determine the damage, not just purely by the economic loss, but the number of deaths or something like that, the different measures. Yeah. And there is one way just to combine those.
Yeah. So we don't do that because each one of the measures is equally important. So we don't do it.
Thank you.
Okay. Any other comment? No question? From online? Yeah. Kotsuki-sensei.
Thank you very much for nice talk. I'm very interested in the crying wolf effect. Okay. So you mentioned that you showed the first evidence, the crying wolf effect exists in the world. And so actually, how did you measure that?
Yeah. So yeah, that's quite a great question. And then what we found is there's several evidence. So for instance, this one is just we found the correlation between the false alarms 6 months before the flooding and the flood damage. Using considering the other important elements which contribute to the flood damage. But there are kind of, different level of the evidences. For instance, in the more like a case study base, they have a questionnaire survey, so that it's quite an interesting. But you can directly ask the people how good the GMA is, right? And then the accuracy, they are kind of how to say, the subjective understanding of the accuracy and the economic damage or their behavior when the flood occurs. You can also compare it. And so those kinds of, there's different level of the understanding of quantification of the Kraivov effect. I just give you the 2 examples.
Okay, I got it. And the second question is, that may relate to the so-called moral hazard. So if maybe we issue the warning too much, so that may make the citizens more optimistic. And so if we think about our Moonshot program, so sometimes I'm wondering whether we should be too optimistic to explain about our, technology for citizens.
Yeah.
So that may reduce the interest for climate change or there is concerns about heavy rains or typhoons in future.
Yeah.
But we also need to somehow sometimes we need to explain the visions or optimistic perspectives for keep doing research. And so do you have any ideas how should we
that's a quite
present?
a different
difficult question.
Open question, but I learned these lines of the research that whenever we deliver something to the people, we change the people, right? Yeah. So we are just saying it, and then if you say something big, I feel good, right? But but you are delivering something to change the people, right? So that and also the people will respond to us, and that changes us. So we need to carefully think that the word, our word, how our word will change the people and society. So that's one kind of lesson, but that's what everybody can say, right? But that's what I'm thinking.
I got it.
Very interesting talk.
Thank you.
The mic is on.
It's on?
Yeah, it's on.
Okay, sorry. The interesting concept is the coupled system, weather and society coupled system. In the physical world, we have many coupled systems like atmosphere, ocean, coupled system, blah, blah.
Yeah.
Of course, I think we cannot construct a physical model for this kind of weather society coupled system. But out of the big data thing, data-driven AI-based coupling system, we can make the AI-based model to do some prediction on weather society coupled system, I think. So you introduced this kind of concept, and I think throughout this project, I hope to see some result on real AI-based weather society coupled system for the prediction model.
Okay, thank you. That's quite encouraging. So these kinds of work will be introduced into the process model. So we like to understand the process and then integrate the process. But as you said, that maybe it's very difficult to model the society just by the process-driven way. So we need to use a lot of data like a human behavior, but rather so we need to do such kind of things. Maybe we can solve quite a complex problem, which is weather society coupled system. Yeah, thank you.
No more questions? Okay, thank you very much, Dr. Sawada.